Welcome to today's video. During the last few videos, we explored multivariate analysis and multivariate differentiation. In particular, we introduced partial derivatives, we introduced directional derivatives, and finally the notion of total differentiation. Today, we are finally going to see how all of these are connected. So our question is, what is the relation between total differentiation, partial differentiation, and maybe directional derivatives? And we're going to look at this question in depth today, and hopefully are going to find a good answer. So, let's take a note. Question. So the question today is, what is the relation between total differentiation and partial derivatives, and in particular the gradient? We have already seen that partial differentiation is usually not sufficient for total differentiation. So a function that has partial derivatives or even directional derivatives in all directions does not have to be totally differentiable. But what about the reverse of this? So let's consider a function that is totally differentiable. What about the partial derivatives of this function? Is there a connection between the total derivative and those partial derivatives? So let's have a look at that first. Consider a function that is differentiable. So, differentiable function f at some point x star. And we'll denote the total differential by g, so let g be the vector gamma 1 to gamma n. And we'll let this be equal to the total differential of f at x star. Okay, then we know that by definition, f of x is equal to f of x star plus g times x minus x star, so that is the linear approximation, plus a small remainder r of x minus x star, where the limit as x tends to x star of that small remainder r of x minus x star divided by the distance of f and x star, so the norm of x minus x star, that limit is 0. And now let's consider the ith partial derivative and see what we can say about that. Let us now take a look at the ith partial derivative of f at x star again. Okay, so that partial derivative df dxi at x star, by definition, that is the limit as lambda tends to 0 of the following expression, we're taking f evaluated along the line through x star in the direction ei, so the ith coordinate. So we have f of x star plus lambda ei, and that expression here, this is the line through x star in direction ei. Then we're subtracting f at x star, and we're dividing by lambda. So that's the definition of one-dimensional differentiation. Okay, so that's the limit we're looking for. And of course, what we can do is we can take this expression here, this f of x star plus lambda ei, and substitute the formula for the total differential here. So let's say we're setting x to be x star plus lambda ei. And then we're using the formula for the total differential. What do we get? And of course, the limit stays the same. Write that 1 over lambda here in front of the expression. And then we replace that f of x star plus lambda ei by that total differential here. So that's f of x star plus g times the difference between x and x star plus r evaluated at x minus x star. Okay, so what we have is f of x star plus g times x is x star plus lambda ei, and then minus x star, plus r at x star plus lambda ei minus x star. And then of course we copy the rest of the expression, that's just minus f at x star. Okay, so what you can see here is a lot of things can be simplified. So we have this f of x star here and minus f of x star here. Those two will cancel out. Then what remains here inside of the g is the x star cancels out, so lambda ei remains, and of course the same is true for the expression inside of r. So we are left with g at lambda ei plus, g times lambda ei of course, plus r at lambda ei. And that divided by lambda. Well, finally, g times lambda ei, g times ei, that just means we're selecting the ith coordinate of g. So effectively that is lambda times gamma I plus this expression r at lambda ei over lambda. So in effect we're getting gamma I plus the limit of r lambda ei over lambda. Okay, so what about this limit here? Well, as we know, the absolute value of lambda is the same as the norm of x star plus lambda ei minus x star. And remember this first expression here, that was x, so that's the norm of x minus x star. So in fact what we have here is this limit r lambda ei over the absolute value of lambda as lambda tends to 0. That is just the limit in the definition of the total differential. It's just the same as this limit here. And that limit is 0. So that's also true here. Okay, and now if that limit is 0, then of course the limit above is also 0. So r lambda ei over lambda needs to be 0 as well, as lambda tends to 0. So what does that mean? Well, final conclusion. df dxi at x star is exactly gamma I. And that is exactly f prime at x star, and then taking the ith coordinate of that. So, conclusion. If a function is differentiable, totally differentiable at some point x star, then the partial derivatives are just the components of the total differential. Or in other words, the partial, or in other words, the gradient is basically equal to the total differential. Okay, so that's our conclusion. If f is differentiable at x star, then the total differential f prime at x star is the same as the gradient at x star. One minor annoyance here, I need to transpose the gradient. I haven't talked about that a lot in the former videos, in previous videos. I'll talk some about that in one of the next videos. So the reasons for this will become clear. What you need to remember is the gradient is usually a column vector. The total differential is the same, but as a row vector. So those are transposed versions of each other. As I said, the reasons for this will become clear in one of the next videos. Okay, so that's the takeaway message here. If a function is totally differentiable, then it also has partial derivatives. It also is partially differentiable for all directions. And the partial derivatives are just the components of the total differential. So in other words, if we want to compute a total differential, then we can just use the partial derivatives. We just need to be sure that the total differential actually exists. So let's write down these findings in a theorem. And then we'll also sum up the reverse direction. That's a little more complicated. But basically there is a reverse direction. More about that in a minute. So let's say we have a set X that is open, subset of the R to the N. Let X be open. Let f be a function defined on X with values in R. And let X star be a point in X. Then our first finding is something that we didn't discuss a lot. You do remember that in one-dimensional theory there was a connection between differentiability and continuity. And with the findings that we have now, one can easily show that this same connection holds in a multivariate analysis as well. If a function is differentiable, then it also is continuous. So let's quickly note that. If f is differentiable at a point x star, then f is also continuous at x star. The second is what we just found out. If a function is differentiable, then it's also partially differentiable and the gradient transposed is equal to the total differential. So if f is differentiable at x star, then f is also partially differentiable at x star. With the gradient of f at x star transposed being the total differential of f at x star. The third point is probably the most interesting one, and that's the reverse direction. So what if f is partially differentiable? Well, we have already seen that there are functions that are partially differentiable, but not totally differentiable. So that's not sufficient. We need to add a little more to that. And the condition that we need here is continuity. So the exact theorem here is if f is partially differentiable and the partial derivatives are all continuous, then f is also totally differentiable. So let's write this down. If f is partially differentiable, and we need this condition not just at the point but in some neighborhood of that point, so on some delta neighborhood and delta x star of x star, and if all partial derivatives df dxi, and those are now functions defined on that neighborhood to R, if those are continuous at x star, then the function f is in fact totally differentiable at x star. Then f is also totally differentiable at x star, and f prime at x star is again the gradient at x star transposed. Okay, so that is the major point here. Basically, partial differentiation and total differentiation are equal if all the partial derivatives at the point in question are continuous. And if you remember the examples that we had where the partial derivatives existed but the function was not totally differentiable, those were also examples for non-continuous functions. And we've talked about those as well, yeah? So the point here was always the partial derivatives were not continuous at the point in question, and that's why this didn't work out. In most practical cases, however, this continuity at every or almost every point will not be a problem. So for most practical cases, we can easily work with that theorem here and just compute the total derivative through the total differential through the partial derivatives. You just have to make sure that the partial derivatives are continuous, so this can actually work. Okay, one last point I'd like to add to the theorem because it's such a good fit. We've already seen that if we take in second partial derivatives, in many cases, if we differentiate it by some xi first and then by some xj, the order of that differentiation did not really matter. So whether we differentiate it by xi first and then by xj, or by xj first and then by xi, didn't make a difference. And in fact, there's a theorem that says in most cases this will not make a difference. And again, continuity here is key. So that's the last point I'd like to add. If all second partial derivatives exist and are continuous, then the order of differentiation for those second partial derivatives does not matter. Yeah, so that can spare you quite some work. If all second partial derivatives of f exist and are continuous on some delta neighborhood again, and delta of x star, then if we take in the second partial derivative with respect to xi and xj, dxi, dxj, okay, at x star, that is then equal to the second partial derivative with respect to dxj, dxi at x star. And that holds for all indices ij. Okay, this condition is also known as Schwartz theorem. Okay, so what that says is basically usually if you take second partial derivatives, the order does not make a difference, provided that the results are all continuous. If they aren't, then there could be different second partial derivatives. Okay, but usually the order does not make a difference. So what this does is basically it helps us, it gives us a tremendously easy tool to compute total differentials, because we just need to take partial differentials, partial derivatives, and we know how to do this. That's easy. That's one-dimensional differentiation. We know that. So we can just do that. We can see if the results are actually continuous, and if they are, then we're good. We know the function is totally differentiable, and we even have the differential. So all that complicated computation with taking the limits and so on, that is not necessary anymore as long as we have our one-dimensional differentiation under control. And hopefully we do. Okay, so that concludes this introduction. In the following videos, we're going to talk a bit about differentiation rules. And of course, there's one big step ahead of us. We have to generalize all this theory to vector value functions. So far, we have only talked about functions with real values in the codomain. But what about functions that have vector values, that map to vectors instead of just real numbers? I will tackle that in one of the next videos. So I'll see you then.